Hi everyone, my name is Amir, and today I'll be presenting our work titled Algorithmic Recourse under Imperfect Causal Knowledge, a Probabilistic Approach. This is joint work with Julius von Kugelgen, Bernard Schilkhoff, and Isabel Valera at the Max Planck Institute for Intelligent Systems. The problem setting we consider is as follows. We have d real-valued features x, a binary target or label y, a given black box classifier h, and a dataset of n observations xi. Consider an individual, visually shown on the right, or factual instance xf, which obtained a negative prediction from the classifier, in this case was rejected a loan from the bank. In this work, we aim to answer why did the individual not get the loan, and what could they have done, or what could they change to get a favorable outcome in the future. A popular framework to solve this problem is that of counterfactual explanations, which follows the counterfactual notion of Lewis as the closest possible world, as is shown in the figure on the right. The approach solves this optimization problem, aiming to identify the nearest instance to the factual instance on the other side of the decision boundary. This approach implicitly assumes independently manipulable features go into the classifier. An alternative framework which we adopt here is that of algorithmic recourse, which is based on the structural counterfactual framework of Pearl. This approach instead shifts the focus to finding minimum cost interventions, which leads to a change in the label. The objective is thus to find an action A on a subset of the variables such that the counterfactual value under this action lies on the other side of the decision boundary. This framework inherently accounts for causal relations between the features and for the consequences of those actions. Thus, changing one feature can have consequential effects on others, possibly leading to more efficient actions. Now, to reason formally about structural counterfactuals, we adopt the SCM framework of Pearl, which consists of a pair of structural equations S and the distribution over background variables P of U. S is a set of deterministic assignments determining the value of each variable xr as a function of its direct causes or causal parents x parents of r and the unobserved or latent background variables u of r. We further assume causal sufficiency and do not consider the cases with hidden confounding. A three-variable example in the top right shows how the structural equations S and the distribution over background variables P of U induce a distribution over observed variables x1, 2, and 3. A structural counterfactual may be computed using the three-step abduction action prediction procedure of Pearl as shown on the bottom right. Importantly, the abduction step relies on the specification of the SCM, which is often not available in practice. Thus, our work starts with a negative result. Unless the set of all acted upon variables is empty, recourse can, in general, only be guaranteed if the true SCM is known. The proof goes as follows. We can construct two SCMs which are indistinguishable from observational and empirical data, but imply different counterfactuals. Thus, the assumption of prior works, which assumed knowledge of the true SCM, is rather restrictive. So a naive approach that takes a point estimate of the SCM, for example via linear regression, can suffer from overfitting or misspecification. And as shown in the previous works, this may lead to suboptimal or infeasible recourse. In this work, we ask, what can be done if only the causal graph is known, but structural equations are not? And the intuition is, since we can no longer give guarantees in this setting, our emphasis is on probabilistic approaches, which achieve recourse with high probability. We first provide an overview of the two approaches. In the first approach, we propose individualized recourse recommendations based on counterfactuals. The assumptions include knowledge of the causal graph, causal sufficiency, and also additive Gaussian noise for the structural equations, which is necessary to perform counterfactual reasoning. We use a Gaussian process, or GP, over the functions in the SCM to average over infinitely many causal models, obtaining a counterfactual distribution as shown on the bottom. In the second approach, we relax assumptions further, leading to a subpopulation-based notion of recourse, which is an interventional rather than a counterfactual quantity. We make no further assumptions about the form of structural equations and instead compute the average treatment effect, or CATE, to find actions that work well on average for a group of individuals similar to the individual for which we seek recourse. In more detail, for the first individualized approach, we model the SCM with a GP prior with the functions fr. We further assume additive Gaussian noise, and this combined with some nice properties of GPs enables us to derive some key quantities in closed form. In particular, given a factual observation, we can average all the different models to obtain a posterior over noise, and thus to obtain a counterfactual distribution for actions of this form, where we intervene on some variables xi, setting them to theta. We then propose to solve instead the following probabilistic version of an individualized recourse problem, where we again minimize the cost such that now the expected classification be larger than some threshold. So the point counterfactual was replaced with an expectation with respect to a counterfactual distribution, where we allow the threshold to depend on the intervention itself and also take into account the uncertainty in the estimation. This form of threshold can be interpreted as a lower confidence bound and is controlled via the conservativeness hyperparameter gamma LCB, which can be increased to guarantee that the recommended actions lead to recourse with high probability. In the second approach, because we do not make additional assumptions, we cannot learn an SCM for counterfactual reasoning, and thus have to resort to interventions. In particular, we compute the average effect of an action on a subpopulation defined by the shared value of all non-descendant variables of the intervened upon variables. For example, we can consider a group of female engineers in their 40s and try to figure out actions that work on average for this subgroup. In our settings, and subject to our assumptions, we can show that the interventional distribution of interest can be identified from purely observational data as a product of conditionals of each variable given its causal parents. Thus, we proceed to learn these conditionals from the given dataset using, in our case, a conditional VAE, but of course, other choices are possible as well. We then propose to solve the similar subpopulation-based recourse problem, where we again minimize cost, subject to a constraint that is now taking the expectation with respect to the interventional distribution over the subpopulation of similar individuals. In order to solve these probabilistic optimization problems for achieving recourse, we first observe that both forms are relatively similar. In fact, they only differ in the distribution with respect to which the expectation of the classifier is taken. In the individualized case, it's the counterfactual distribution, and in the subpopulation case, it's the interventional distribution. We also note that we need to select two different quantities to select a recourse action, the intervention targets as well as the intervention values. The interventional targets are the subset of variables upon which we choose to act. For this combinatorial problem, we can either enumerate different subsets or for a large number of variables take something like a greedy approach. For the interventional values, which are the values we pick for the interventional targets, we can either discretize the continuous space and use a brute force approach, which seems like the only choice for non-differentiable classifiers, or for differentiable classifiers, we can also use a gradient-based approach, first reformulating the constraint optimization problem using this Lagrangian here. Then we can tackle the saddle point problem with stochastic gradient descent, using the reparameterization trick to push the gradient with respect to the interventional value theta through the expectation. This is possible because both the GP model in the individualized approach and in the implicit density model in the subpopulation-based approach admit such a reparameterization. Finally, for a given set of intervention targets, we can select the optimal interventional values, theta. We perform a number of experiments comparing the proposed approaches on a number of synthetic and semi-synthetic SCMs. In the interest of time, we suffice to pointing out some trends. Number 1. Probabilistic recourse approaches lead to more robust results than point-based recourse approaches, which lose in validity once their untestable assumptions are no longer met. 2. Subpopulation-based approaches, as compared to individualized approaches, lead to lower validity at slightly higher cost. This is reasonable because subpopulation-based approaches try to achieve recourse for a whole group of individuals. And finally, we show how the conservativeness hyperparameter gamma LCB allows our probabilistic approaches to trade off cost against validity, and thus gives some more control over the level and type of recourse actions desired. As a take-home message, recourse can only be guaranteed under perfect causal knowledge. In practice, probabilistic approaches can be used to relax our assumptions to give recourse with high probability. There's an inherent trade-off between the kind of assumptions we're willing to make and the level of individualization. Specifically, if we don't assume a particular form in the SCM, we can no longer provide individualized recommendations. In future work, we are excited to consider extensions to heterogeneous features beyond real-valued ones, and to explore more efficient optimization over intervention targets. We would also like to further relax our assumptions to account for confounding variables or only partially specified causal graphs. With that, I thank you very much for your attention, and if this sounded interesting to you, please come chat with us some more at the virtual poster session, or visit our paper on arXiv. We also plan to soon release a user-friendly codebase, so watch out for that. Thanks.